Hi everyone. This is going to be a lesson about diagonalization for linear algebra. So please make sure that you are comfortable with the previous lesson about the characteristic equation, finding eigenvalues and eigenspaces, because we're going to need to use that for this section also. All right, so let's get started. All right, so diagonalization. We're going to start this section with some definitions right away. Definitions. We're going to say a diagonal matrix is a square matrix whose non-diagonal entries are all zero. So I think we've talked about diagonal entries before. We mean the main diagonal. So first, let me show you some examples. Examples of diagonal matrices. Well, whatever I make has to be square. Let's do some 3 by 3 examples. So for example, the matrix with 1, 2, 3 on the main diagonal and zeros everywhere else. That's a diagonal matrix. I guess the identity matrix would be another example. How about this one? How about 4, 0, 0, 0, 0, 0, 0, 0, 4? That is also a diagonal matrix. It satisfies the definition. All of the non-diagonal entries are zero. In fact, I could make a matrix where every entry is zero, and it would still be called a diagonal matrix because the non-diagonal entries are all zero. So it is okay if some of the diagonal entries are zeros as well. But they don't have to be. It could be like 1, 2, 3. So I said definitions. That was just the first one. Next, we're going to say if A and B are n by n matrices, A is similar to B if there exists an invertible matrix P such that A equals P, B, P inverse. I'm going to add something to this as well. But A is similar to B if there exists an invertible matrix P such that this is true. So A is on the left-hand side, B is on the right-hand side, but it's sandwiched in between P and P inverse. Or, equivalently, B equals P inverse AP. I think we could get from one of these equations to the other just by, multiply both sides by P on the right and multiply both sides by P inverse on the left. And that's how you get from the first equation to the second. So they are equivalent to each other. So, yeah, in this case, B is on the left side and A is on the right-hand side, sandwiched in between P inverse and P. So I just want to address here before we move on that similar, this is a new concept for us, and it's not the same as saying that two matrices are equal. If you say two matrices are equal to each other, they have to have all the same entries in all the same positions. This is also not the same as saying that two matrices are row equivalent. Row equivalent is a different concept where you get from one matrix to the other by doing row reduction steps. So we have lots of different concepts of two matrices being related to each other. You could have two matrices that are equal, two matrices that are row equivalent, or now you could have two matrices that are similar. Those all mean different things. All right, and now our third and maybe the most important definition of this section. A is called diagonalizable. If A is similar to a diagonal matrix, which we will call D. Given A, the process of finding D and P is called diagonalizing. A. So we say we are going to diagonalize the matrix A. What we mean is we're going to find a diagonal matrix that it is similar to. And, you know, in order for it to be similar, we need to also find this matrix P, this invertible matrix P that shows up. So we want A equals P D P inverse. So we'll do a 2x2 example of this. Actually, I haven't really told you how does this process work? Like, how do we find D and P? Well, we'll talk about that. But before we do that, we're going to do an example where we just verify that A equals this 2x2 matrix, -4, -6, 3, 5, can be diagonalized to A equals P D P inverse, where this problem is going to give us those matrices. It's going to say that P equals this 2x2 matrix, -1, -2, 1, 1. And D is the 2x2 matrix. Well, this has to be a diagonal matrix, right? So you know the non-diagonal entries have to be zeros. The other entries are going to be 2 and -1. So this problem just wants us to verify. So it already gave us all the matrices. You know what? In order to verify that this is true, this equation here, A equals P D P inverse, we have A, we have P, we have D. We need P inverse, don't we? It wasn't given. So first, let's find P inverse. So it's a 2x2 matrix that's given to us. So you know how to find the inverse of a 2x2. You do 1 over the determinant times, and then, right, we have a little trick. You think of those as A, B, C, D, and this is going to be 1, 2, -1, -1. What's the determinant of this? -1 minus -2. So -1 plus 2 is the determinant. Anyway, altogether, I get, yeah, so the determinant, that's 1 over the determinant is just 1. So this is just 1, 2, -1, -1. So anywhere in this problem that we need the inverse, that's the inverse. Now we can actually check that that equation is true. So we're going to check this thing here, right? A equals PD P inverse. So here's A. Does it equal, I'm going to write all of them out. Does it equal this times this times this? Where what I've written here is A equals P times D times P inverse. We'll check this. We'll check to see if this is true. But this is, you know, I wrote it all out like this so that you could see this is what it looks like for a matrix to be diagonalizable. The matrix A being diagonalizable means that it is similar to a diagonal matrix. So this is a diagonal matrix, and it's sandwiched in between some kind of matrix P and its inverse. Okay. So let's check. We just have to check the right-hand side. So the right-hand side, we could do some matrix multiplication. You know, let's multiply the first two matrices. Or you know what? Actually, it's up to us. Do you want to... We know that this is associative, so we could multiply the first two times each other and then multiply by the third. Or we could actually multiply by the second and third matrix and then multiply by the first. For some reason, that's how I did it in my notes. So I have -1, -2, 1, 1. And then I multiplied this times this. I don't know why I did it that way, but it works either way. So when you're multiplying three matrices, you know, do the first two first, or you do the second and third. So I got 2, 4, 1, 1, like that. And then I did that matrix multiplication, and I found that that does get me -4, -6, 3, 5, and that does equal A. So 2 matrix multiplications in order to check. It seems like sometimes in this class when we have a new concept, sometimes I do a problem where I kind of give us the answer and I just have us sort of verify it. But the big question should be, well, how would you find these? Like if you were just given A and you were wondering, first of all, is it diagonalizable? You know, is it similar to a diagonal matrix? And then second of all, how do we find them? So let's write some questions here. And these are kind of the main questions for this lesson. Is first of all, given A, how do we know if A is diagonalizable? You know, do you think that all square matrices are diagonalizable? Do you think just some square matrices are? We'll talk about that. Number 2, if A is diagonalizable, how do we find P and D? I'm not including P inverse in this question because I think if we find P and D, then we know how to find P inverse. So it's really just a question of how do you find those two? And number 3, why is diagonalization useful? We'll see a use for it. We'll get to all 3 of these questions, but before we can answer them, we need some theorems. We haven't had any theorems in a while. So, theorem 4. if n by n matrices, A and B, are similar, then they have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. Okay. So I don't really know if this seems surprising or not. I mean, we have this definition of similar that we just introduced, but the definition didn't really say anything about eigenvalues or characteristic polynomial. But yeah, it turns out similar matrices have the same characteristic polynomial. And then, the roots of the characteristic polynomial are the eigenvalues, so they have the same eigenvalues, same multiplicities. It does not necessarily mean that they have the same eigenvectors, like the same eigenspaces, because, to find the eigenvectors, the eigenspaces, you would still have to go back to those original matrices, A and B, which might not be the same. So, anyway, let's prove this. We haven't done a proof of a theorem in a while. So, proof. Suppose B equals P inverse AP. So I'm supposing that I have two matrices that are similar. Okay. Then let's start with the determinant of B minus lambda I, because that is going to be the characteristic polynomial of B. So I want to show that the characteristic polynomial of B, ultimately, I'd like to show that it equals the characteristic polynomial of A. All right, so we'll show some steps here. This equals something, equals something, equals something, and we're hoping to arrive at the determinant of A minus lambda I. Here's what I'm going to do. I'm going to introduce, if B is supposed to be P inverse AP, then let's rewrite this as P inverse AP. And I'm also going to do another little trick here. Instead of writing I, I'm going to write P inverse times P. We know that that equals I, right? A matrix times its inverse has to equal I. That's actually going to be useful for us because now I look at this and both of these terms involve P inverse, so we could factor P inverse out from the left. A P minus lambda P. And in fact, this thing that I just wrote, we could factor a P out from the right because they both have a P on the right. So we could say the determinant of P inverse parentheses A minus lambda I, and then a P on the right. Now, I'm not finished yet. Let's remember, what are we trying to get to? I'd like this to equal the determinant of A minus lambda I. This thing we just wrote involves A minus lambda I, but there's this other stuff attached to it. So we have to figure out what to do about that. So what have we got here? We've got the determinant of a matrix times a matrix times a matrix, right? We could think of this as the determinant of something times something times something. We actually had a property of determinants a while ago. And I want to say that this was back when we had a lesson called properties of determinants, that when you do the determinant of a product, you can actually split this up into a product of determinants. So it could be the determinant of the first piece times the determinant of the second piece times the determinant of the third piece. Which in the textbook, that was probably, I think, probably section 3.2, whichever one had properties of determinants. So what can we do with this? Now, these are just numbers, right? The determinant is a number times a number times a number. We know that that could be done in any order, right? You could rearrange multiplication of real numbers so that you could do this one times this one times this one. Multiplication is commutative for real numbers. And now these two things can actually be combined. I guess I need to do this on a new page. By doing the reverse of that property that I just did a minute ago, we could merge those together into that. So you see, this is pretty clever because now this piece here is the determinant of I times the determinant of this stuff. Well, the determinant of I is just 1 because when you have a triangular matrix, the determinant is the product of the diagonal entries, and the diagonal entries are all 1s. So these are all 1s, and this entire thing equals the determinant of A minus lambda I. So what we have shown is that the characteristic polynomial of B is equal to the characteristic polynomial of A. So we proved it. And we did this by using the fact that they were similar and this property of determinants. So that's pretty cool. So if two matrices are similar, they have the same characteristic polynomial and the same eigenvalues. What does this do for us? What does this theorem do for us? Well, since, I'm going to go back to that previous 2 by 2 example, since -4, -6, 3, 5 is similar to the diagonal matrix 2, 0, 0, -1, they have the same eigenvalues. All right, from the theorem that we just said, similar matrices have the same eigenvalues. Can you see what the eigenvalues are? Yeah, from the diagonal matrix, you can tell. The eigenvalues are 2 and -1. So 2 and -1, how did I get that? This is by theorem 1. That was in our lesson where we introduced eigenvectors and eigenvalues. Theorem 1 in the textbook is in section 5.1. It basically said if you have a triangular matrix, the eigenvalues are the entries along the main diagonal. So this is definitely triangular, so the eigenvalues are 2 and -1. So this is pretty cool because what if we wanted to find the eigenvalues of this 2 by 2 matrix? We know how to do that. We know how to find characteristic polynomial and all of that. But if we knew that it was similar to this, we get the eigenvalues immediately. In general, if A can be diagonalized, I use the word if, so that means not every matrix can be diagonalized. But if A can be diagonalized to D, Then the diagonal entries of D are the eigenvalues of A. So that means that if a matrix is diagonalizable, then it has to be, lambda 1, lambda 2. We don't know how many of them there are, right? And I'm trying to be general here. We'll say up to lambda n. And all the other entries are zeros. So I guess I just told you how to find the matrix D. You could find the eigenvalues. But how would we find P? To fully say that we diagonalized a matrix, we need to find D and P. And before I can tell you how to find P, we need two theorems to get there. So first of all, oh, you know what? Actually, I think we may have discussed this theorem already. So theorem 2, I think we may have said this already, but we'll say it again, okay? I think that we talked about this in 5.1, but let's say it again because we're going to use it. If an n by n matrix A has eigenvectors v1 through vr corresponding to distinct eigenvalues lambda 1 through lambda r, then the set v1 through vr is linearly independent. So I may have said this theorem near the end of section 5.1, the lesson on eigenvalues and eigenvectors. I don't think we used it for anything. I think we may have said this theorem and then just moved on and not really used it. Or if we didn't say the theorem, then we're saying it now. Now is when we actually need this. So yeah, when you find eigenvectors and eigenvalues and you've got different distinct, different eigenvalues and different eigenvectors, the set of those eigenvectors is linearly independent. Let me show you an example. For example, this was a 2x2 problem that we did a couple of lessons ago. But this 2x2 matrix has this eigenvector corresponding to lambda 1 equals 2, and this eigenvector corresponding to lambda 2 equals 3. So the set -2, 1, -1, 1 must be linearly independent. I think we could also tell that that's linearly independent for other reasons. but I'm saying this is a new reason why that set must be linearly independent because of theorem 2. Now, this is because these eigenvalues are different. Because they're distinct, 2 and 3. So we're going to use this, but now we're ready for a new theorem, a big theorem. I think the previous lesson didn't have any theorems in it, so this is making up for that. This is theorem 5, and it has a name. You know, most of the theorems in this class don't have names, so when there is a name, you know it's an important one. This is called the diagonalization theorem. Okay, with a name like that, it must be important. And it's going to take us a little while to write this, actually. So it says an n by n matrix A is diagonalizable if and only if it seems good already, right? Doesn't this seem like a good theorem already? If and only if A has n linearly independent eigenvectors. Furthermore, A equals P D P inverse with D a diagonal matrix if and only if there are going to be two things here. If and only if the columns of P are n linearly independent eigenvectors of A. And the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors forming P. Okay, so the theorem takes up the whole screen. Let's take some time to think about this. So you remember earlier when I said that there were 3 big questions for this lesson? This theorem answers questions 1 and 2. Let's write that. Note, this answers our questions 1 and 2. Because question 1 was if we're given a matrix A, how do we know if it's diagonalizable? This answers that right at the beginning. And then question 2 was, okay, if it's diagonalizable, how do you find P and D? Well, this tells us. This is how you find P. It's the n linearly independent eigenvectors of A. We know how to find eigenvectors. And then how do you find D? Well, it's a diagonal matrix where the diagonal entries are the eigenvalues. Now, what's this business here about corresponding respectively to the eigenvectors forming P? What this means is that when we form the matrix P and we form the matrix D, we have n linearly independent eigenvectors, and we have n diagonal entries of D. They have to go in the same order. That's all this means. Here, you know what? Real quick. Up here, you know when we had this example? We would put these two eigenvectors together. If we say this one comes first and this one comes second, then we have to do this eigenvalue first and this eigenvalue second. That's all we mean when it says they correspond respectively. Match up the same order. If you call this one number 1 and this one number 2, you have to call this number 1 and call this number 2. If you flip them around, you could flip these two around, but then you also have to flip these two around. That's what it means. All right, let's go. Let's actually do this. Let's see. Let's do this with this one then, okay? That same 2 by 2 example. So A equals 1, -2, 1, 4. I don't need to actually rewrite the eigenvector and eigenvalue. We just pointed to them up there on that previous page. So I'm going to say that it has A equals P D P inverse, where if we found the eigenvectors and eigenvalues, let's put this together. The eigenvalues were 2 and 3, so let's put them on the main diagonal of D and make the other entries 0. I chose to put the 2 first and the 3 second. That means that P is going to be made up of those eigenvectors, so we go -2, 1, and then -1, 1. Because the theorem says the columns of P are the n linearly independent eigenvectors of A. By the way, this is kind of a by the way. Notice that we know P is invertible because without even finding the inverse, without even trying to find the inverse, or without even finding the determinant, how do I know that P has to be invertible? It's because its columns are linearly independent. So that was one of the facts in the invertible matrix theorem. All right, so we've covered the definition of similar. We've talked about what it means for a matrix to be diagonalizable. It means it's similar to a diagonal matrix. The theorem basically tells us that if we know how to find eigenvectors and eigenvalues, we can check and find out if a matrix is diagonalizable, and we can actually diagonalize it. We can find P and we can find D. So what we haven't done yet is talk about what is this used for. So let's do an application. Writing A as PDP inverse helps us compute A to the K quickly for large values of K. And this is actually used in some real-world applications. In particular, I'm thinking about what would be called iterative methods or discrete dynamical systems, because we have this fact that a to the k equals p d to the k p inverse. Now, you can prove this fact if you'd like. I think that the textbook shows this for a specific 2x2 case, but it actually does work in general. And, when we say a to the k, we're talking about a matrix times itself k times. So, like, a squared would be a times a cubed would be a times a times a. But what happens if you want to do a raised to a really large number? Are you going to have to do matrix multiplication over and over and over and over again? Well, this fact actually helps us because raising d to the k is much easier than raising a to the k because d is diagonal and has a lot of zeros in it. So that's the idea behind this. So also, if d equals, say, lambda 1, lambda 2, dot, 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 all the way down to lambda n, with zeros for all the other entries, then it turns out that d to the k, this is for diagonal matrices. All you have to do is raise each one of these to the k for a diagonal matrix. And I'll say for any positive integer k. That's really what we're interested in, because I said that we're interested in large values of k. So yeah, I'll show you an example. But I hope that you appreciate that, doing this d to the k by this fact is a lot easier than like multiplying a matrix times itself a bunch of times. All right, let's look at an example. Sorry, I just had to get some more paper here. All right, example. Let's suppose we're given a 2x2 matrix. 1, 2, 4, -1. It's not the same matrix as earlier. Oh, you know what? Let me see here. I don't know if I want to do this one, because I guess we haven't really diagonalized this one. Maybe we should do the other one. Yeah, I think I'm going to change this. Actually, let's do the matrix from earlier. It was pretty close to that, wasn't it? I guess it was 1, -2, 1, 4. All right, so let's say we're given that matrix, and the question is, what is a to the 100? So let's think about this. I'll walk us through this process. Now, we could do a times itself 100 times, a times a times a times a, but we'd be here forever, right? So note, a to the 100 equals a times a times a 100 times. And it's a 2x2 matrix, so you have to do matrix multiplication over and over. It would be very time consuming. That's what I'm trying to get across. So instead, a to the 100 is equal to p d p inverse to the 100, which is equal to p d to the 100 p inverse. This is really using the fact from above, which we didn't really prove, but I'm using this. Now, for this matrix A, we know what P is, we know what D is. I don't know if we found P inverse, so let's find P inverse. So here, I'll write over here, D we said was this, and P we said was this, -2, -1, 1, 1. I just don't know if we have found P inverse. So 1 over the determinant of P times, and then what do we want to do here is swap these around and like this. So the determinant of P is going to be -2 minus -1 minus -1, so we could just say +1. So I guess the determinant looks like it's -1. So when we write this out, we're going to get -1, -1, +1, +2. Let me section this off, okay? This was some work we had to do to find P inverse. This is D and P, so we have all of the pieces of the puzzle. And now let's use this. So a to the 100 is P D to the 100, P inverse, and that is going to look like -2, -1, 1, 1. Okay, what's D to the 100? Well, 2 to the 100, 0, 0, 3 to the 100, and then P inverse. -1, -1, 1, 2. Is this easy to do? 2 to the 100 and 3 to the 100? No, I mean, 2 to the 100 is a gigantic number, and 3 to the 100 is a gigantic number. But it's kind of easier than doing this. It's easier than that. So I'm going to say that the key idea is that we can find a to the 100 by multiplying these three matrices instead of 100 matrices. Matrix times a matrix times a matrix. So we had to find P and D and P inverse, but once you find them, you just have three matrices to multiply, and that's considered much easier than multiplying out A times A times A over and over again. And that was for 100, but you could also apply this to even larger values of K. What if you had to do A to the 1000? It would still just be three matrices. And that's a lot easier than multiplying 1,000 matrices. So this kind of answers our question 3 from earlier about why is diagonalization useful. There are actually real-life situations where you might want to do a matrix raised to a large number. I mentioned earlier something about iterative methods or dynamical systems. Those are areas of study that you might see in another class, but it's when you want some kind of process happening over and over again. We talked about linear transformations that can be represented by a matrix, A. So what if you want to apply a linear transformation over and over and over again? So you multiply by a, and then you multiply by a, and then you multiply by a. So if you want to apply a linear transformation a 100 times, you might have to do a, multiply by it over and over again. Or you could do this. So that's the idea. All right, so I have a problem that I'd like you to try. I'm not going to ask you to raise anything to the 100th power. But I'm going to give you a 2 by 2 problem. So given a equals 1, -2, -2, 1, there's going to be 3 parts to this. Part A, find all eigenvalues. Part B, find 2 linearly independent eigenvectors, if possible. And part C, write matrices P and D such that A equals P, D, P inverse. So I'm asking you to diagonalize this matrix A if possible. I'd like you to pause the video, take a few minutes, and work on this. All right, so do you see that part A and B are basically like things we did in the previous 2 sections? So it shouldn't be too bad. First of all, we need the characteristic polynomial, right? That's what we do to find eigenvalues. So that's going to be a minus lambda I. So it's going to look like 1 minus lambda minus 2 minus 2, 1 minus lambda. The determinant of that. So the determinant of that is 1 minus lambda, 1 minus lambda, and then minus -2 times -2, so minus 4. I know that we're going to wind up setting this equal to 0, so I think it's going to be best if we go ahead and expand this. And then combine the 1 and the minus 4. So we have lambda squared minus 2 lambda minus 3. You can go ahead and just set this equal to 0 right here. I mean, I guess this is the characteristic polynomial. And we want to solve the characteristic equation, so just set it equal to 0 and solve. I'm going to move the problem away now. Let's get that out of the way. This factors. I mean, if the eigenvalues are going to be integers, then this factors. So there's no guarantee that the eigenvalues will always be integers, but it's nice when they are. All right, so we get lambda 1 equals 3. Lambda 2 equals -1. Those are the eigenvalues, which I guess that is everything that part A asked us for. So we're done with part A. I labeled them lambda 1 and lambda 2. You could also have them in the opposite order, and the rest of the problem will still work out fine. Which it's up to you which one you label as lambda 1 and which one you label as lambda 2. All right, part B, we have to do this process for each eigenvalue. So for lambda 1 equals 3, we want to work with the system a minus 3ix equals 0. We want to find solutions to this, get them in parametric vector form. That's going to help us find all the eigenvectors that correspond to this eigenvalue. And usually we've seen that when we do this, we get like a nice augmented matrix with some nice structure to it that's going to give us a free variable. What I mean by that is if you refer back to what A is and you subtract 3 from the diagonal entries, what do you get? You have -2, -2, -2, -2, and a column of zeros on the right-hand side. So when I say that there's a nice structure here, I mean it row reduces to be a pretty simple matrix with a free variable. And then row 1 tells me that x1 plus x2 equals 0, so x1 is equal to -x2. And now I'm ready to write solutions. Solutions are going to look like this, where x2 is a free variable. So we pull x2 out, and the vector that we have is -1, 1. Now, this problem did not tell us we don't have to write a basis for the eigenspace. I know we did that in the previous lesson, but this one just said to find 2 linearly independent eigenvectors. So I'm just going to make a note that an eigenvector is one of the eigenvectors is, oh, you know what? Let's give this a name. I'm going to call it v1. -1, 1. I'm giving it a name v1 so that I remember that it matches up with lambda 1. v1 and lambda 1 go together. Now, we know a bunch of other eigenvectors already, right? You could do any multiple, because x2 can be anything, so you do any multiple of this. However, if I take a multiple of this one, that's not going to give me 2 linearly independent eigenvectors. So in order to find an eigenvector that's linearly independent from this, I need to work with the other eigenvalue, which was -1. This time when I work with A plus IX equals 0, I have the matrix 2, -2, 0, -2, 2, 0. Sometimes when you do these problems, the augmented matrices that you get for each part, sometimes they look, what word do I want to use here? I was going to say sometimes you get matrices that look similar, but I don't want to use the word similar because we have a definition for that. I just want to say that, you know, there's a nice structure to this matrix and there's a nice structure to this matrix. They're going to row reduce nicely. Like, I kind of expect that to happen, right? So this was 1, 1, 0, 0, 0, 0, and this is almost the same. But that slight difference is going to be important. x2 is free again. This time row 1 is telling us that x1 minus x2 equals 0. So you see, this is going to get us something different. It's important that it gets us something different so that we get something that's linearly independent. Let's start a new page. Solutions are going to be, well, we got x1 equals x2. So how do we deal with that? Well, x2 is the free variable, so just say x2, x2, and we still think about it as we're pulling x2 out, and then what vector would have to go here? It turns out that it's going to be 1, 1. So let's move this up. So that's an eigenvector, right? An eigenvector corresponding to this eigenvalue is v2 equals 1, 1. Because these came from distinct eigenvalues, they're going to be linearly independent. So I guess we should just say answer to B. We wanted two linearly independent eigenvectors, and we found them. I guess just say V1 equals this, and V2 equals this. So part C asks us to actually finish the diagonalization process. So A equals P D P inverse. We've already found all of the ingredients for it, right? Where P equals and D equals. Notice that I wrote the two linearly independent eigenvectors right next to each other. It's going to be real easy to use those to form the matrix P. You just use the first one as the first column and use the second one as the second column. Because I did them in this order, I have to make sure that I go lambda 1, lambda 2, which was 3, negative 1. Now, this is my answer. There is also another correct answer that you might have gotten. Remember, when I found the eigenvalues, I found 3 and negative 1, and I labeled them in that order. I said lambda 1 is 3, lambda 2 is negative 1. If you labeled the 3 and the negative 1 in the opposite order, that's okay, but then these two columns of P have to be in the other order. Okay? So I'm going to write that. You don't have to write two different answers because either one of them is a correct answer, but I just want to write this one time. If you flipped the order of the eigenvalues, then you flip the order of the eigenvectors. See what I mean? And you could actually verify that that does work. You know, A equals P D P inverse. I didn't actually go through the trouble of finding P inverse because the problem didn't really ask me to. So we're almost done. We just have one more thing to talk about, I guess. There's something that I think maybe I've been kind of using without explicitly saying, and that's theorem 6. An n by n matrix with n distinct eigenvalues is diagonalizable. And I don't think we're going to prove this one, but I think that this kind of follows from our discussion earlier, and especially from theorem 2, which we stated earlier. I guess theorem 2 talked about distinct eigenvalues giving you linearly independent eigenvectors. And then because you have linearly independent eigenvectors, you can kind of follow from there that the matrix winds up being diagonalizable by theorem 5. So I just wanted to state that. And then one more thing. I want to say that an n by n matrix with fewer than n distinct eigenvalues. Oh, by the way, hold on a second. Hold on, let's not finish the sentence yet. I have a question. Do you think it's possible for an n by n matrix? Do you think it's possible for an n by n matrix to have more than n distinct eigenvalues? Like, could a 3 by 3 matrix have 4 eigenvalues? Well, the answer to that is no. And you could think of this in a couple of different ways. I mean, one way is when you set up the characteristic polynomial, if it's a 3 by 3 matrix, the characteristic polynomial is going to be degree 3. So it has, at most, 3 distinct solutions to the characteristic equation. And, you can apply that to the n by n case. An n by n matrix, you expect the characteristic polynomial to be a degree n polynomial. So you're not going to get more than n distinct eigenvalues, okay? You could have n. We've seen that happen before, like a 2 by 2 matrix with 2 distinct eigenvalues. You could also have fewer than n distinct eigenvalues. That happens when one of the eigenvalues has multiplicity 2 or more. Okay, so you could have like a 3 by 3 problem with only 2 eigenvalues, but one of them has multiplicity. Okay, so now I'll finish this note. If there are fewer than n distinct eigenvalues, it might still be diagonalizable. And for this, I'm going to refer you to an example in the textbook. In this section 5.3, and let's say textbook 5.3, example 3. It gives a 3 by 3 matrix. Oh, I didn't leave myself much room here. I just want to finish this note. You can refer to this in the book, but 1, 3, 3, -3, -5, -3, 3, 3, 1. It's not super important what all the details are, but it actually is diagonalizable. It equals PDP inverse, where for this one, P is 1, -1, -1, -1, 1, 0, 1, 0, 1. But there's actually only 2 distinct eigenvalues. And the diagonal matrix has the repeated eigenvalue. I guess the important thing for whether or not a matrix is diagonalizable is theorem 5, the diagonalization theorem. It says an n by n matrix is diagonalizable if and only if there are n linearly independent eigenvectors. Well, look at this matrix P. Each of its columns came from a set of linearly independent eigenvectors. And that's because the eigenvalue 1 would have an eigenspace with a dimension of 1. So you find an eigenvector corresponding to lambda equals 1. And then for lambda equals -2, for that eigenvalue, you wind up with an eigenspace of dimension 2. So that basis has 2 elements, and then those 2 basis elements are the second and third column. But the reason why this says it might be diagonalizable is because when you get those 2 eigenvectors corresponding to this other one, there's still the question of, are they linearly independent from the first vector? And they might be or they might not be. In this case, they are. So this is an example where it has 2 distinct eigenvalues, but it's still diagonalizable. All right, so that was our lesson on diagonalization. I guess I'll tell you that, in my mind, the lesson we just did and the 2 lessons before it, those three all kind of go together. They're all about eigenvalues, eigenvectors, eigenspaces, characteristic polynomial, and now this concept of diagonalization, which heavily relies on eigenvectors. So I'll tell you that from here on out, the rest of the course is going to sort of sample some various linear algebra topics that we haven't covered yet. So these three lessons kind of went together as one unit, and now we're going to jump around a little bit and cover a few more things before the course is over. So we've got a few interesting topics coming up to look forward to. All right, so that's it for now. And as always, I hope you're doing well, and I'll see you soon.